I want to learn mathematics because I want to use it for astrophysics, physics in general, quantum physics, engineering, a lot of different kinds of engineering, mostly aerospace and mechanical, but also bioengineering and perhaps other fields. So I've been relearning math. But the problem is that when I use traditional mathematics textbooks, they give me rules without explaining why those rules exist. It makes me angry. One perfect example would be the commutative property, is it called? I'm pretty sure, which basically states that of multiplication, the commutative property of multiplication states, if I'm not mistaken, I could be mixing it up with the associative property, they're very similar, but it states that A times B times C is equal to C times B times A, or C times A times B, any order of factors. Which I get when you're multiplying two numbers together. That is simple to me. Because if you have a two-dimensional object with 4 rows of 3, that's the same as 3 rows of 4. That makes sense to me. It both equals to 12. 3 rows of 4 people is 12. 4 rows of 3 people is 12. Same thing. But then when you go into the higher dimensions, third dimension I also get that. It's the same number of blocks. If you have 12 blocks by 12 blocks by 12 blocks, or sorry, those are the exact same number. I should do it with different numbers. Let's make it more simple. If you have 2 blocks by 3 blocks by 4 blocks, it's going to be the same amount of blocks as 4 blocks by 3 blocks by 2 blocks, or what have you, any order. That makes sense too. But what about 10 factors? How do you visualize that in your head? How do you make sense of that? Fucking cat, give me a second. So before I dive back in to algebra and geometry, trigonometry, calculus, differential equations, linear algebra, I want to know why. Because until I know why, it's just going to keep pissing me off. Because I don't like being given rules without being told why I should follow them. Oh my fucking god. I know what you're thinking. Luke hates his fucking cat. And 2 things. First of all, she's not my cat. She is my step cat. Second of all, yes, I do. Yes, I do hate her. I do not abuse her. She abuses me. Every now and then I'll give her a little swat on the head. Not hard. When she really pisses me off. Just a little this. Just that. No more. Okay. Let's move forward. Okay. So I want to learn why all this shit works. So I've got this textbook that was made free by the University of South Carolina. I believe, don't they have a weird ass name, like their mascot? I'm pretty sure it's called a gamecock. South Carolina Gamecocks, yeah. Why the fuck is anybody here from the University of South Carolina? Why the fuck was that the one? You thought, oh, yeah, that's what we're going to call ourselves, the Gamecocks. What is wrong with you? How can you decide to go to a school that calls their mascot that, bro? That is not threatening. It's not, I don't know. You know what? Maybe it's cool. Maybe it is cool. Maybe I'm an asshole. Leave a comment if I'm an asshole. I would love that. I would love that. I'm open to all kinds of controversy. in the comments regarding the South Carolina Gamecocks. Say that with a straight face. Oh God, I'm a fucking child, bro. I'm a fucking child. Say it with a straight face. Right now. On to the math. So I've got this textbook called Mathematical Reasoning. And it's supposed to go into exactly what I'm talking about. Why does all this shit work? At least a little. It's supposed to answer a good chunk of my questions. Why should I believe you when you tell me that A times B times C times D times... what the fuck is the next word in the alphabet? Times E times F is equal to F times D times G. Why am I supposed to believe you? That's what this book kind of goes into. It goes into proofs, logic. I don't know what else. We're going to see. We're going to see what happens. So let's go to the table of contents and jump in. Introduction to writing proofs in mathematics. Statements and conditional statements. Beginning activity 1. Statements. Much of our work in mathematics deals with statements. In mathematics, a statement is a declarative sentence that must have a definitive truth value, either true or false, but not both. A statement is sometimes called a proposition. The key is that there must be no ambiguity. To be a statement, a sentence must be true or false, and it cannot be both. So a sentence such as, "The sky is beautiful," is not a statement, since whether the sentence is true or not is a matter of opinion. A question such as, "Is it raining?" is not a statement, because it is a question, and is not declaring or asserting that something is true. Some sentences that are mathematical in nature often are not statements, because we may not know precisely what a variable represents. For example, the equation 2x plus 5 equals 10 is not a statement, since we do not know what x represents. If we substitute a specific value for x, such as x equals 3, then the resulting equation 2 times 3 plus 5 equals 10 is a statement, which is a false statement. Yeah, because 6 plus 5, that's 11. Which of the following sentences are statements? Do not worry about determining the truth value of those that are statements, just determine whether each sentence is a statement or not. All right, let's do this together. Okay, sorry, I'm just trying to figure out which of these is like, is it for each of these I have to determine? I think so. Which of the following sentences or statements? Do not worry about determining the truth value of those statements. Okay, blah, blah, blah. Okay, cool. This is a statement. That would be either true or false. This is not a statement because it has a variable. We don't know what that variable means. We don't know what that variable stands for. Why isn't a variable a statement? Why isn't it a statement? The equation 2x plus 5 equals 10 is not a statement, since we do not know what x represents. Okay, so we don't definitively know it to be true or false. It can maybe be true sometimes, but not others. So it has an in-between. Okay, so that means it's not a statement. 3 times 5 plus 7 equals 19, that's a statement. There exists an integer x such that 3x plus 7 equals 19. Ooh, would that be a statement? Would that be a statement? I feel like that would be a statement because there is no in-between there. It would either be true or false. It would. Has to be. Either true or false. The derivative of f of x equals sine x is f prime of x equals cosine x. I think that would be a statement. That is either true or false. There is no ambiguity. Does the equation 3x squared blah blah blah, this polynomial equals 0, have two real number solutions? That's a question. That's not a statement. All right. Beginning activity 2, conditional statements. Given statements P and Q, a statement of the form if P then Q is called a conditional statement. It seems reasonable that the truth value of the conditional statement if P then Q depends on the truth values of P and Q. The statement if P then Q means that Q must be true whenever P is true. The statement P is called the hypothesis of the conditional statement, and the statement Q is called the conclusion of the conditional statement. We will now explore some examples. All right. Okay. If it is raining, then Laura is at the theater. Under what conditions is this conditional statement false? For example, sorry, I heard a little movement. I'm paranoid. I'm not paranoid. If it is raining, I swear, if it is raining, then Laura is at the theater. Under what conditions is this conditional statement? Sorry, I'm trying to wrap my mind around this a little bit. If it is raining, so if it's raining, that's the hypothesis, I guess, then Laura is at the theater. I figured this whole thing would be a hypothesis, but I guess not. If it's raining, raining is P, Laura at the theater, that's Q, right? I would guess so. Under what conditions is this conditional statement false? For example, is it false if it is raining and Laura is at the theater? No. That would make it true. Is it false if it is raining and Laura is not at the theater? Yes, that would make it false. Is it false if it is not raining and Laura is at the theater? I would say no. I would say it's not false then, because it's not necessarily saying that Laura's at the theater only if it's raining. It's saying that if it is raining, Laura is definitely at the theater. So she could be at the theater at other times, right? Is it false if it is not raining and Laura is not at the theater? No, that would also make it true. C would neither make it true nor false. A would make it A would make it true, right? Yeah, raining, Laura's at the theater. Yeah, that would make it true. Not raining, Laura is at the theater. That would make it neither true nor false. D, I think, would make it true. Oh, wait. Under what conditions is it false? I think D would make it true, right? Well, I guess not necessarily. The combination of it's not raining and Laura is not at the theater would make it maybe true if we had every single case of it raining and every single case of Laura being at the theater. We would have to have every single case so that we could know. And we would have to know whether those cases are verifiable and, like, known to be true, if that makes sense. Anyway, is it false if it is raining and Laura is not at the theater? Yes, I would say B. It's B. If there's only one answer, I would say it's B. I don't think any of the other statements would make it false, since A would make it sort of true, and D would make it sort of true. C neither makes it true nor false, I would say, because of what I've already, the reasoning I've already given you. So I'm going to say B. Is it false if it is raining and Laura is not at the theater? That's the only one that would truly make it false. Identify the hypothesis and the conclusion for each of the following conditional statements. Okay, if X is a positive real number, so all this is P. That would be the hypothesis. And that then root X is a positive real number. That would be the conclusion. If root X is not a real number, that's P. Root X not a real number, then X is a negative real number. That's our conclusion. X is a negative real number. If the lengths of the diagonals of a parallelogram are equal, this is our P, this whole thing. The lengths of the diagonals of a parallelogram are equal. That is our P, that is our hypothesis. Then the parallelogram is a rectangle. The parallelogram is a rectangle. You assuming I'm a human. What I gotta do to get it through you? I'm superhuman, innovative, animated, rubber, so that anything you say is ricocheting off of me and it'll glue to you. I'm devastated more than ever, demonstrating how to give a motherfucking audience. Sorry, I had to do a little mouth training. The parallelogram is a rectangle. That is our conclusion. Can I just do that whole Eminem verse just to prove to you that I can do it? Sumalama dumalama, you assuming I'm a human. What I gotta do to get it through to you? I'm superhuman, innovative, animated, rubber, so that anything you say is ricocheting off of me and it'll glue to you. I'm devastating more than ever, demonstrating how to give a motherfucking audience a feeling like it's levitating, never fading, and I know the feeling is forever waiting for the day that they can say I felt to be celebrating, because I know a way to get them motivated. You mean like fuck. I messed it up. I was almost there, though. That was almost the end. I'm not going to do it again, I promise. I know I'm annoying the shit out of you. Statements. As we saw in beginning activity 1, some sentences that are mathematical in nature often are not statements because we may not know precisely what a variable represents. Following are some more examples. There exists a real number x such that x plus 7 equals 10. This is a statement because either such a real number exists or such a real number does not exist. Yes, that means we got that one previously right when we were looking at which of the following were and weren't statements. In this case, this is a true statement since a real number does exist, namely x equals 3. For each real number, x, 2x plus 5 equals 2 times x plus 5 halves. That would also be a statement. I mean, I guess these are all statements. We already know that they are. This is a statement since either the sentence 2x plus 5 equals 2 times x plus 5 halves is true when any real number is substituted for x, or it's false. That makes sense. Solve the equation x squared minus 7x plus 10 equals 0. That's not a statement because it's a directive. It's a demand, a command. I don't know the difference between a demand and a command. I don't know if there is one. English is a weird language. A plus b squared equals, I'm going to try to I looked at it. Not a statement. I was going to try to guess. A plus b squared equals a squared plus b squared. Not a statement because we don't know the variables. We don't know what they represent. However, the sentence, there exists real numbers a and b such that a plus b squared equals a squared plus b squared is a statement. Now, would this be a statement if every single solution, every single integer exists for every single integer for each of these variables would yield an equality? Would that make it a statement? I'm guessing not, because the variables still represent values outside of mathematics itself. Maybe. Like A has to stand for something. It has to represent something. We don't know what it represents. All right. Compare the statement in the previous item to the statement for all real numbers a and b, a plus b squared equals a squared plus b squared. That is a statement. This is a false statement since there are values for a and b for which they do not equal each other. For example, if a equals 2 and b equals 3, then a plus b squared equals 5 squared equals 25, and blah, blah, blah. Cool. All right, progress check 1.1. Bro, I feel like we just did a progress check. Which of the following sentences are statements? Do not worry about determining the truth value of those that are statements. Just determine whether each sentence is a statement or not. Okay. 2 times 7 plus 8 equals 22. This is a statement. Definitely. It's either true or false. No in between. 2x plus 5y equals 7. That is ambiguous. It's not either true or false, I would say, given what we've read. I do think there might be an argument if every single integer would make this true in the entire totality of numbers, then we might say this is a statement. But we'd still have to know what x and y represent, right? Okay, 3. There are integers x and y such that 2x plus 5y equals 7. That would be a statement. This is either true or false. Given a line L and a point P not on that line and in the same plane, there is a unique line in that plane through P that does not intersect L. That is a statement. It's either true or false. 5. A plus b cubed equals a cubed plus 3a squared b plus blah, blah, blah. That would be not a statement because we don't know what a and b represent. We don't know what numbers, we don't know what they represent. So it's ambiguous whether it's true or false. 6. For all real numbers a and b, a plus b cubed plus blah, 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 blah. Okay, so this is kind of what I was talking about. This is what I was talking about when it comes to, like, if every single real number yields an equality. But I guess for that to be a statement, you would have to include this part for all real numbers A and B, at least for conventional purposes. Maybe you don't have to, but that's what most people do. That's what it's agreed upon. So sometimes it's good to follow conventions like that to reduce confusion amongst collaborators. So I would say this is a statement because it's either true or false. 7, does the equation 3x squared, so like, because this would not be a statement even if all real numbers A and B yield an equality, because it's ambiguous. I guess. Does the equation 3x squared minus 5x minus 7 equals 0 have two real number solutions? That's a question. If ABC is a right triangle with a right angle at vertex B, and if D is the midpoint of the hypotenuse, then the line segment connecting vertex B to D is half the length of the hypotenuse. That is a statement. That is definitely a statement. It's either true or false. 9, there do not exist. Right. Hold up. Let me get a more decent grip on this. You have a right angle at vertex B. D is the midpoint of the hypotenuse. Then the line segment connecting vertex B to D is half the length of the hypotenuse. Yeah, I would say that's a statement. And I think it's a false statement because the line segment connecting vertex B to D, that would be from the right angle to the midpoint of the hypotenuse. So maybe that is half the length. I don't really know. I'm not very good with trigonometry. COVID happened right in the middle of when I was taking trigonometry. So I understand like half of it. Anyway, 9, there do not exist three integers x, y, and z such that x cubed plus y cubed equals z cubed. That would be a statement. That's either true or false. How do we decide if a statement is true or false? In mathematics, we often establish that a statement is true by writing a mathematical proof. To establish that a statement is false, we often find a so-called counterexample. These ideas will be explored later in this chapter. So mathematicians must be able to discover and construct proofs. In addition, once the discovery has been made, the mathematician must be able to communicate this discovery to others who speak the language of mathematics. We will be dealing with these ideas throughout the text. Okay, all right. Very good. For now, we want to focus on what happens before we start a proof. One thing that mathematicians often do is make a conjecture beforehand as to whether the statement is true or false. Right. Okay. This is often done through exploration. So a conjecture meaning like a guess. I'm guessing. I'm making a conjecture. That a conjecture means guess. The role of exploration in mathematics is often difficult because the goal is not to find a specific answer, but simply to investigate. Following are some techniques of exploration that might be helpful. Techniques of exploration: guesswork and conjectures. Formulate and write down questions and conjectures. When we make a guess in mathematics, we usually call it a conjecture. Cool, so it does mean guess. Examples. Constructing appropriate examples is extremely important. Exploration often requires looking at lots of examples. In this way, we can gather information that provides evidence that a statement is true, or we might find an example that shows the statement is false. This type of example is called a counterexample. For example, if someone makes the conjecture that sine 2x equals 2 sine x, for all real numbers x, we can test this conjecture by substituting specific values for x. One way to do this is to choose values of x for which sine x is known. Okay. All right, cool. So you don't have to make the calculation. You just already know that the value of x for which sine x is known. You already know that. Using x equals pi over 4, we see that sine 2 pi over 4 equals sine pi over 2 equals 1. And 2 sine pi over 4 equals 2 root 2 over 2 equals root 2. Since 1 does not equal root 2, these calculations show that this conjecture is false. I'm not going to really go into the depth of this specific mathematical equation because that's not really what we're learning right now. We're not learning trigonometry right now. We're learning statements. Since 1 does not equal root 2, these calculations show that this conjecture is false. However, if we do not find a counterexample for a conjecture, we usually cannot claim the conjecture is true. The best we can say is that our examples indicate the conjecture is true. As an example, consider the conjecture that if x and y are odd integers, then x plus y is an even integer. We can do lots of calculations, and this is usually considered true. Odd numbers usually add up to even. We can do lots of calculations, such as 3 plus 7 equals 10, and 5 plus 11 equals 16, and find that every time we add two odd integers, the sum is an even integer. However, it is not possible to test every pair of odd integers, and so we can only say that the conjecture appears to be true. We will prove that this statement is true in the next section. Interesting. I wonder how we're going to do that. Use of prior knowledge. This is also very important. We cannot start from square one every time we explore a statement. We must make use of our acquired mathematical knowledge. For the conjecture that sine 2x equals 2 sine x, for all real numbers x, we might recall that there are trigonometric identities called double angle identities. We may even remember the correct identity for sine 2x, but if we do not, we can always look it up. I don't really remember identities that well. We should recall or find that for all real numbers x, sine 2x equals 2x sine x cosine x. We could use this identity to argue that the conjecture for all real numbers x, sine 2x equals 2 sine x is false, but if we do, it is still a good idea to give a specific counterexample as we did before. Yeah, so you can't just use prior knowledge to disprove something with a different formula that is known to be true, because both could be true. But it points you in the right direction, perhaps, to ultimately make the proof. Kind of how correlation doesn't equal causation, but it could suggest causation. So it makes it a good reason to explore the possibility of causation. Like for artificial sweeteners, like as people who consume artificial sweeteners are more likely to be unhealthy, so that suggests that you should explore causation. Doesn't necessarily mean that causation is there. That's one thing that really pisses me off, just as a side tangent. Every time somebody claims that artificial sweeteners are bad for you, they look at those correlational studies. It pisses me the fuck off, because it's fucking correlation, you dumbass. It's correlation. I'm sorry. If you believe that artificial sweeteners are bad for you, I'm not calling you dumb. I'm calling you a person who jumps to conclusions, in my opinion. If you believe that they're bad for you because of these studies on gut microbiome causation and what it does to the microbiome, I might be more inclined to listen to you. I'm sorry. That's not the topic of this video. It's not the topic of this video. All right. We already read this. Sorry. I need to stop going on tangents. Next, cooperation and brainstorming. This is another example of generating conjectures, I guess. Working together is often more fruitful than working alone. When we work with someone else, we can compare notes and articulate our ideas. Thinking out loud is often a useful brainstorming method that helps generate new ideas. Putting your heads together, essentially. Progress check 1.2, explorations. Use the techniques of exploration to investigate each of the following statements. Can you make a conjecture as to whether the statement is true or false? Can you determine whether it is true or false? All right, a plus b squared equals a squared plus b squared for all real numbers a and b. All right, how do I make a conjecture about that? I guess we'll use the techniques of exploration. So let's try to think of a counterexample for a plus b squared equals a squared plus b squared. Let's just think of a random number. Let's think of 2. A plus b squared equals 4 squared if both equal 4. Let's do different numbers. Let's do 2 and 3. So a equals 2, b equals 3. So 5 squared equals 25. 2 squared equals 4. B squared, or 3 squared equals 9. 4 plus 9 is 13. So we got 13 on the right side. What do we have on the left side? 3, or 2 plus 3 equals 5. 5 squared is 25. So I just thought of a counterexample. 25 does not equal 13. So this statement is false through counterexample. Or at least I can make a conjecture for such. I'm pretty sure if you find a counterexample, and then that immediately means it's false. But if you find an example, and that doesn't immediately make it true. Okay, 2. There are integers x and y such that 2x plus 5y equals 41. So for this, we just need to prove one example. So one counterexample isn't necessarily going to falsify this because it's just saying that integers do exist. They're just saying that the integers exist. Not necessarily that every single integer equals up to 41 when you plug it in. So, can we think of an example here? If we do, this is a little tough, but let's do y equals, let's say 7, maybe. So 5 times 7 equals 35. 35 plus something equals 41. That would have to be an odd number, though. 41 minus 35 is, no, 41 minus 35 is 6. So if x equals 3, then it's true. 5y, so 5 times 7 is 35. 2 times 3 is 6. So if x equals 3 and y equals 7, then yeah, there are integers x and y. So I just proved this via example. If x is an even integer, what are the other methods? Should I use any of these other ones? Use of prior knowledge, I guess, but that's just to make a conjecture. All right. If x is an even integer, then x squared is an even integer. This one might be a little bit more tough. My use of prior knowledge, I can use my use of prior knowledge here and say that when you multiply odd numbers together, I can think of a counterexample, I think. Wait, but that's if it's an even integer, not if it's an odd integer. Like, so 3 times 3, that's 9. That's not even, but it's not an even integer in the first place. But when you have 4 times 4, that's 16. And I know that my use of prior knowledge tells me that any even number plus another even number equals an even number. And when you multiply something by itself, you're just adding that number to itself for as many times. You're multiplying that number by itself x number of times. You're multiplying x by its adding x to itself x number of times. Sorry. Or no, you're adding it to itself 2 times. No, you're not. I'm an idiot. That's 2x. That's 2x. You're just multiplying it by itself. Meaning you add it to itself x number of times. Yes, okay. Sorry. So that, I would say that's probably true, but because I can't think of a counterexample. I don't have anyone to cooperate with here. I'm alone right now. Maybe you in the comments, anybody in the comments want to think of a counterexample, any prior knowledge that says that it's false or true, anything like that. But through all the methods here, I would say that this is probably true, but I can't prove it. If x and y are odd integers, then x times y is an odd integer. I don't know. I think I can maybe think of a counterexample to this. I'm trying to think of one. 3 times 5 is 15. I'm just going to go through all the multiples of 3, I guess you would call them. 3 times 7 is 21. 3 times 9 is 27. 3 times 11 is 33. Times 13 is fucking 39. And if we keep going up through the odd multiples of 3, we're just going to keep adding 6 is what we're doing. So got 39, 45, 51, 57. And if you keep adding an even integer to an odd integer, you're just going to keep getting an odd integer from my prior knowledge. So I'm going to say this is probably true. Probably true, because if you're multiplying odd integers, then maybe not though. Maybe not. Let's do 9. Let's do an easier one. Let's do 5. Wait. Oh, I think that's true too. 5 times 1 is 5, times 3 is 15, times 5 is 25, times 7 is 35. That just keeps going up in more orders of 10. So you're also adding and keep adding an even integer to an odd integer. So you're going to keep getting an odd number. So I think this statement might be correct. I can't think of a counterexample. My prior knowledge is telling me that it's true. I'm going to say it's true. It's probably true. All right, conditional statements. I thought we already went over this, but it's the new section. We had our first encounter with conditional statements in beginning activity 2. Since conditional statements are the most important type of statement in mathematics, we give a more formal definition. Definition. A conditional statement is a statement that can be written in the form if P then Q, where P and Q are sentences. For this conditional statement, P is called the hypothesis and Q is called the conclusion. Intuitively, if P then Q means that Q must be true whenever P is true. Because conditional statements are used so often, a symbolic shorthand notation is used to represent the conditional statement if P then Q. We will use the notation P arrow to Q to represent if P then Q. When P and Q are statements, it seems reasonable that the truth value, true or false, of the conditional statement P arrow Q depends on the truth values of P and Q. There are 4 cases to consider. P is true and Q is true. P is true and Q is false. P is false and Q is true. P is false and Q is false. And I believe, if I'm not wrong, I would say that P is true and Q is false would be the only statement, would be the only example that would falsify the conditional statement. It would be the only outcome. P is true and Q is true would truthify it, would add to the truth. It wouldn't make it automatically true. It wouldn't prove it true. P is false and Q is true doesn't necessarily falsify the statement, because Q could be true under other conditions, but also always be true when P is true. P is false and Q is false, that would just help to truthify the statement. Now, the conditional statement P arrow Q means that Q is true whenever P is true. It says nothing about the truth value of Q when P is false. Okay, good. So we got that right. Using this as a guide, we define the conditional statement P arrow Q to be false only when P is true and Q is false. So that would be, yep, P is true and Q is false. Okay, cool. So we got that right too. That is only when the hypothesis is true and the conclusion is false. In all other cases, P arrow Q is true. This is summarized in table 1.1, which is called a truth table for the conditional statement P arrow Q. In table 1.1, T stands for true and F stands for false. So the only false statement would be P is true and Q is false. That's the only thing that would make the statement false. Table 1.1, blah, blah, blah. The important thing to remember is that the conditional statement P arrow Q has its own truth value. Okay, all right. It is either true or false and not both. Its truth value depends on the truth values for P and Q, but some find it a bit puzzling that the conditional statement is considered to be true when the hypothesis P is false. We will provide a justification for this through the use of an example. Example 1.3, suppose that I say, if it is not raining, then Daisy is riding her bike. We can represent this conditional statement as P arrow Q, where P is the statement, it is not raining, and Q is the statement, Daisy is riding her bike. Although it is not a perfect analogy, think of the statement P arrow Q as being false to mean that I lied, and think of the statement P arrow Q as being true to mean that I did not lie. Okay, we will now check the truth of P arrow Q based on the truth values of P and Q. Suppose that both of them are true, that is, it is not raining and Daisy is riding her bike. In this case, it seems reasonable to say that I told the truth and that P arrow Q is true. Suppose that P is true and Q is false, and that it is not raining and Daisy is not riding her bike. It would appear that by making the statement, if it is not raining, then Daisy is riding her bike. Wait. Fuck. That kind of confused me. Suppose that P is true, and if it is not raining, right. What in the name of fuck? It's probably just somebody outside. Okay. We're just going to keep going. If it is not... All right, suppose that P... I'm sorry, I'm getting a little confused here. I'm guessing some of you are too. Suppose that P is true and Q is false, or that it is not raining and Daisy is not riding her bike. It would appear that by making the statement, if it is not raining, then Daisy is riding her bike, I have not told the truth. So in this case, the statement P arrow Q is false. Now suppose that P is false and Q is true, or that it is raining and Daisy is riding her bike. Did I make a false statement by stating that if it is not raining, then Daisy is riding her bike? The key is that I did not make any statement about what would happen if it was raining. So I did not tell a lie. So we'd consider the conditional statement, if it is not raining, then Daisy is riding her bike, to be true in the case where it is raining and Daisy is riding her bike. I would say that doesn't make it true. I guess it does. But it just, I would say it's a non-contributing factor. It's a non-contributing example. I wouldn't necessarily say it makes the conditional statement true. I guess it does. Certainly doesn't make it false. Finally, suppose that both P and Q are false. That is, it is raining and Daisy is not riding her bike. As in the previous situation, since my statement was P arrow Q, I made no claim about what would happen if it was raining, and so I did not tell a lie. So the statement P arrow Q cannot be false in this case, and so we consider it to be true. Cool. Sounds good. Progress check 1.4, explorations with conditional statements. Consider the following sentence. If x is a positive real number, then x squared plus 8x is a positive real number. Although the hypothesis and conclusion of this conditional sentence are not statements, the conditional sentence itself can be considered to be a statement, as long as we know what possible numbers may be used for the variable x. From the context of this sentence, it seems that we can substitute any positive real number for x. We can also substitute 0 for x, or a negative real number for x, provided that we are not willing to work with a false hypothesis in the conditional statement. Okay, so we can substitute x for 0 or a negative number, but that does not, but if those examples turn out to be false for the conclusion, if they make the conclusion false, it does not prove the conditional statement to be false because they do not match the hypothesis. I guess that's what he's saying. I feel like he's kind of saying it a little weird. In chapter 2, we will learn how to be more careful and precise with these types of conditional statements. All right, A. Notice that if x equals -3, then x squared plus 8x equals -15, which is negative. Does this mean that the given conditional statement is false? No, it does not. It doesn't prove the statement true either, but it just doesn't match the hypothesis. That's not what the statement is saying, because x is not a positive real number. So the hypotheses don't match. B, notice that if x equals 4, then x squared, I'm not going to verify these calculations, I'm just going to assume that he's telling the truth. Then x squared plus 8x equals 48, which is positive. Does this mean that the given conditional statement is true? It doesn't prove it true, I would say, but it is a qualifying example that makes it true. It is a true thing. So yes. I wouldn't say it means that the given conditional statement is true. I wouldn't say that, but if we're going by the convention that this book is establishing, then yes. C, do you think this conditional statement is true or false? Record the results for at least 5 different examples where the hypothesis of this conditional statement is true. All right, so x is a positive real number, then x squared plus 8x is a positive real number. So a positive real number multiplied by itself, I figure is always going to be a positive real number. I can't prove that right now, but it makes a lot of sense. Any positive number of things, if you have a positive number x rows of x is going to be a positive number. It just makes sense. And then plus 8 rows of x, and x is a positive number, that's also a positive number. So I definitely think it's true. I definitely think it's a true statement. Record the results for at least 5 different examples where the hypothesis of the conditional statement is true. I don't really think we need to do that. I think that's just a waste of time. 2. If n is a positive integer, then n squared minus n plus 41 is a prime number. Remember that a prime number is a positive integer greater than 1, whose only positive factors are 1 and itself. To explore whether or not this statement is true, try using and recording your results for n equals 1, 2, 3, 4, 5, and 10. Then record the results for at least 4 other values of n. Does this conditional statement appear to be true? All right, let's do 1. 1 minus 1 plus 41. Yeah, I think that's a prime number. I'm pretty sure. I can't think of any factors beside 1 and 41 that lead to 41. For 2, 2 squared is 4. Minus 2 is 2. Plus 41 is 3. That's, I'm pretty sure, a prime number. 3 squared, 9, minus 3 makes it 6. Plus 41 makes it 47. That would also be a prime number, if I'm not mistaken. 4 squared is 16. Minus 4 is 12. Plus 41 is 53. I believe that's a prime number. 5 squared is 25. Minus 5 is 20. That makes 61 for the polynomial. What did I say that makes? Fuck. What did I say that makes? 25, 61. I'm pretty sure that's a prime number. 10. 10 squared is 100. Minus 10 is 90. Plus 41 is 131. I'm pretty sure that's a, wait, is that a prime number? I think it's a prime number. 132 would be 12 times 11. But 131, I don't think of anything. Can't think of anything. Then 4 other values of n. Let's say, let's just do the other single digit numbers. Let's do 6. 6 squared, 36. Minus 6 is 30. Plus 41 is 71. Pretty sure that's prime. 7 squared is 49. Minus 7 is 42. Plus 41 is 83. Is 83 prime? I'm pretty sure it is. Let's do 8. 64 minus 8 is 56. Plus 41 is 97. Pretty sure that's prime. 9. 9 squared is 81. Minus 9 is 72. plus 41 is what? 72 plus 41. 70 plus 40 is 110, plus 1 is 111, plus 2 is 113. I'm pretty sure that's prime. So it does appear to be true, at least for all the single-digit numbers. Can't prove that it is true. It appears to be true. Further remarks about conditional statements. The conventions for the truth value. It makes sense that we're doing so much about conditional statements. He did say that it is the most important type of statement in math. The conventions for the truth value of a condition of convention. Blah. The convention. Do I have to do the Eminem verse again, you think? I'm not going to do it. The conventions for the truth value of conditional statements may seem a bit strange, especially the fact that the conditional statement is true when the hypothesis of the conditional statement is false. The following example is meant to show that this makes sense. I feel like we've already we've already gone over this. Do we really need to go through it more? I don't think so. At least not for me, so I'm not going to do it. If you want to pause the video and go through this, go ahead. I'll put it right here. Go ahead, pause the video. The fact that there is only one case when a conditional statement is false often provides a method to show that a given conditional statement is false. In progress check 1.4, you were asked if you thought the following conditional statement was true or false. If n is a positive integer, then n squared minus n plus 41 is a prime number. For many values of n, it does turn out to be a prime number. However, if we try n equals 41, we get blah, 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 41 squared. Oh, wait. So in the case where n equals 41, the hypothesis is true. 41 is a positive integer, and the conclusion is false. 41 squared is not prime because 41 times 41 equals 41 squared. Oh, man. I wish I would have thought of that. I feel like I could have cracked that if I thought about it long enough. Huh. Interesting. Therefore, 41 is a counterexample for this conjecture, and the conditional statement is false. There are other counterexamples, such as n equals 42, n equals 45, n equals 50, but only one counterexample is needed to prove that the statement is false. Interesting. I thought maybe that would turn out to be true. That statement. Although one example can be used to prove that a conditional statement is false, in most cases, we cannot use examples to prove that a conditional statement is true. Yeah, because a true statement doesn't necessarily make it true, especially if it's saying, like for all natural numbers or for all positive integers. Like, you would have to check every single positive integer if that's part of the hypothesis. For example, in project check 1.4, we substituted values for x for the conditional statement. If x is a positive real number, there we go, that's what I was just talking about, then x squared plus 8x is a positive real number. For every positive real number used for x, we saw that x squared plus 8x was positive. However, this does not prove the conditional statement to be true because it is impossible to substitute every positive real number for x because numbers are infinite. So although we may believe that this statement is true, to be able to conclude that it is true, we need to write a mathematical proof. Methods of proof. So if you get a counterexample for a conditional statement, you can prove it false. But if you get a true statement for a mathematical proof, that doesn't necessarily mean that you are proving it to be true. Methods of proof will be discussed in section 1.2 and chapter 3. Awesome. Wait, section 1.2? Have we not gotten to? Yeah, we're still on 1.1. Okay. Progress check 1.5, working with a conditional statement. Sometimes we must be aware of conventions that are being used. In most calculus texts, the convention is that any function has a domain and a range that are subsets of the real numbers. In addition, when we say something like the function f is differentiable at a, it is understood that a is a real number. With these conventions, the following statement is a true statement, which is proven in many calculus texts. If the function f is differentiable at a, then the function f is continuous at a. Using only this true statement, is it possible to make a conclusion about the function in each of the following cases? It is known that the function f, where f of x equals sine x, is differentiable at 0. I'm guessing so. Function f, it is known that the function f, where f of x equals sine x, is differentiable at 0. I don't know, actually, because the hypothesis is if the function f is differentiable at a, then the function f is continuous at a. So this doesn't have to do with the true statement. The hypothesis is actually different. If f of x equals sine x, then it's differentiable at 0. That doesn't have to do with this true statement. The hypothesis doesn't match, I would say. The function f, where f of x equals the cube root of x, is not differentiable at 0. I would also say that that doesn't have to do with the hypothesis of that one specific true statement. 3, it is known that the function f, where f of x equals absolute value of x, is continuous at 0. What's the true statement again? If the function f is differentiable at a, then the function f is continuous at a. So is the function f of x equals absolute value x, is that differentiable at 0? If you remember what an absolute value function looks like, if it's just f of x equals absolute value of x, it's a v. It goes down and it hits 0 when x equals 0, and then it goes back up for all of the positive numbers. So it's making a V shape. So the derivative is, I don't think it would be defined. And I forget how to calculate derivatives mathematically. Using only this true statement, is it possible to make a conclusion about the function in each of the following cases? I would say for this, if I'm only using that true statement, I would say it is not possible to make a conclusion, because I would also have to know a true statement about whether f of x equals absolute value of x is differentiable at 0, and it doesn't say whether it is. I'm guessing. Wait a second. Hold up. I think I got wrong what the question is exactly asking. Using only this true statement, is it possible to make a conclusion about the function in each of the following cases? What conclusion are we making? I don't know exactly. Let's go through it again and try to make any kind of conclusion, I guess. It is known that the function, and you'll see what I mean. It is known that the function f, where f of x equals sine x, is differentiable at 0. So, wait a second. I think I'm dumb. Yeah. If it's known, if this is true, wait. If it is differentiable at 0, if it's known, if I know that it is differentiable at 0, then yes, I can make the conclusion, given only that true statement, that the function is continuous at 0. 2. It is known that the function f, where f of x equals cube root of x, is not differentiable at 0. So I would say, if I know this, if I know that f of x equals cube root of x is not differentiable at 0, then I would say it's not possible to make a conclusion about the continuity of the function because the hypotheses don't match. Not differentiable at 0. So I'm guessing But if we're following the convention of true and false statements, then if the hypotheses don't match, it automatically renders the conditional statement true in that case. So I'm going to say yes, we can draw a conclusion, a truth conclusion, regardless of whether this function is continuous or not. Right? Okay. I could be wrong there, actually, but I think I'm right, given what this book has already disclosed. It is known that the function f, where f of x equals absolute value of x, is continuous at 0. Does that mean that the function is differentiable at 0? I would say no. I would say no, because it doesn't, the hypothesis doesn't make any conclusion about what happens when the differentiable, when the function does not have a differentiable at a. It only says what happens when the function is differentiable at a. Oh wait, but we're talking about continuous. Oh God, Jesus. But it also does not make a conclusion what happens when the function is continuous. It only makes a conclusion, the hypothesis only states what happens when f is differentiable at a. So we cannot draw a conclusion, I don't think. But it also does not falsify this truth statement, or that conditional statement. It is known that the function f, where f of x equals absolute value of x over x, is not continuous at 0. So I would say that that would render this statement true in that case. Certainly doesn't falsify it, because it doesn't match the hypothesis of if f is differentiable at a. But we can't determine whether the function, whether the derivative, whether the function is differentiable at 0. We can't determine whether it's differentiable at 0. I don't know if I'm solving this problem right, but that's my interpretation of the question. Oh, that was confusing. I'm sorry about that. That was a little confusing. And honestly, now my brain's kind of fried. It's a little fried after that. And we're almost done anyway, so I might just wrap this up for the time being, because we've been at this for what, an hour? Yeah, an hour and 3 minutes. I think it's time to stop. My name is Luke. This is Castles in the Air. This channel is called Castles in the Air because I have a lot of goals, a lot of very different, very ambitious goals that are completely untold whether I will actually achieve them. One of them is to become an expert mathematician, an expert engineer, and an expert physicist in many different realms of those subjects. And I don't know if I'll actually ever get there, but I'd like to get there, and I'm trying. And so it's like I'm trying to build castles in the air with no foundation. It originates from a quote from Henry David Thoreau, I believe. Yeah. That's it. That's all. Goodbye.